Hi everyone, hope you're doing well. Today we're going to look through the homework questions that were due last week. I'm giving a little bit of time each kind of week to make sure people have had as much chance as possible to work through the questions before uploading these videos, because otherwise you might be tempted to just watch it. And again, the learning value really comes from trying the questions, working through them. And there's no point just watching this video unless you've tried the questions. Okay, so first I'm going to deal with the higher level questions, and I'll have a separate video for the ordinary level ones. So without any further ado, let's get cracking. The focus is still on mechanics, because remember, this is a core area of the course which you really should solidify and make sure you're confident on. Okay, so let's get cracking. State Newton's laws of motion. The first law of motion is that an object will stay in a state of rest unless an external force acts on it, or if it's moving at steady velocity, it will keep moving at a velocity. The second law is that a object would accelerate in the direction of an applied force, and the direction of when a force is applied to an object, it'll accelerate in that direction with acceleration proportional to the force. And the third one is that for any, the colloquial one is for every action there's an equal and opposite reaction, but we have to be a bit more detailed and say that when body A exerts a force on body B will exert an opposite and equal force on body A. That's 12 points just for knowing Newton's three laws. Show that F equals ma is a special case of Newton's second law. They love asking this, so it's really good kind of thing. One of the derivations that they often ask. So let's start off with the definition of a force. Force is proportional to a change in momentum over time. So the change in momentum is the momentum before the mass of the object times its velocity times the minus the initial. So the mass times its initial velocity, all divided by the time it took for that change in momentum. Now, if you look at the top line, we've got m in common for both of these. So let's take that out. V minus u, over t. Force is proportional to, I've just taken mass out because it's common to the top. Now, if you remember, v minus u over t, well, that's in final speed minus final velocity minus initial velocity divided by time, otherwise known as acceleration. So we have force is proportional to mass times acceleration. And our final step here is to get rid of this proportional. So the force is equal to some constant proportionality k multiplied by ma. And because of our definition of the units, 1 Newton is the force required to give a mass of 1 kilogram and acceleration of 1 meter per second squared. So the k is 1. So k is 1 by our definition of our units. So F equals ma, proven. And again, very popular derivation, 10 points, low hanging fruit, make sure you're picking them up. Or from the tree, I suppose. Anyway, let's see, onto a more meaty kind of calculation one. A skateboarder with a total mass of 70 kilos starts from rest at the top of a ramp and accelerates down it. The ramp is 25 meters long and is an angle of 20 degrees to the horizontal. The skateboarder has a velocity of 12.2 meters per second at the bottom of the ramp. Now, there's a couple of ambiguous parts of this question. The first is that the 25 meters is this distance here. The hypotenuse, not the horizontal distance. It's the physical distance traveled. The second one, which we'll get to in a few minutes, is when they talk about him accelerating, him or her, that it isn't really clear if they propel themselves or if they rely purely on gravity. So that's kind of ambiguous and a bit vague at the moment. So let's look. They've nicely structured this for us, part 1, 2, and 3. So first, calculate the average acceleration of the skateboarder on the ramp. Okay, well, let's think about what we know. We know, let's just do a suvat on this. We know the displacement was 25 meters. We know that the skateboarder's final velocity was 12.2 meters per second. What else do we know? We also know that he was at rest at the beginning, 0 meters per second. That's a bit of a presumption here, but it's the only way to solve this, because otherwise we don't have everything we need. Okay, so let's think about the suvat equations. We got V equals U plus AT. S is equal to UT plus half AT squared. And V squared is equal to U squared plus 2AS. These are the ones I asked you to memorize this week of the derivations. And in relation to that, make sure that you know where to find them in the logbooks as well. So, if you don't remember the derivations, at least you can apply the formula. Now, speaking of which, what are we looking for here? We're looking for A. We have an S, we have a U, we have a V. So you have to make sure you know to choose which of these equations is going to be useful. So V equals U plus AT. It's got A, which is what we're looking for, but we unfortunately don't know t, so we'd have two unknowns. That's not going to be any use to us. S equals ut plus half at squared. Again, we don't know what t is, so that's not really going to be much good to us here. But the third one is the way to go, because we have the final velocity, we have the initial, and we have the displacement, and we have the unknown thing we're looking for. So let's start there. So start off always by writing out the equation. Then rearrange it. So we're looking to isolate a, that's what we're looking for, the acceleration. So we're going to bring the u squared across. V squared minus u squared is equal to 2as. I'll do it step by step. So now we're looking to get a on its own. So let's bring this 2s across. It's multiplied on this side, divided on this side. V squared minus u squared divided by 2s will give us our acceleration. Now we have everything we need. We have our equation rearranged. Let's put in the numbers. V squared, so that's 12.2 to v squared. Initial velocity was 0, so minus 0. Divided by 2 by the displacement, which is 25, so 2 by 50, gives us an acceleration of 2.9768 meters per second squared. Now, as always, make sure you include your units, otherwise you're throwing away a mark when you don't need it. So that's the first part done. Find the component of the skateboarder's weight that is parallel to the ramp. I'll just put this under here because we might need it in a moment. So the component of his weight. Now let's just think of what's happening. We've got the ramp. There's the skateboarder. Artistic skills are lacking. And that skateboarder has a weight, which is vertical. And that weight vector can be broken down into two components. The component that is perpendicular to the plane and that is parallel. And we're looking for the parallel one. And that's where we get the angle that it makes with the horizontal, and its sine of the angle it makes multiplied by the magnitude of the vector in total. So let's get the weight in total first. His weight, or her weight, is 70 kilos times the acceleration due to gravity, which is 686 newtons. And the component of that which is parallel to the plane is times sine of 20. So I'm going to keep that answer in my calculator. Times sine 20 gives me a component of 234.625 newtons. I'll keep all the precision, why not? So that's how much of the skateboarder's weight is bringing them down the ramp. That's part 2. Finally, find the force of friction acting on the skateboarder on the ramp. Okay, well let's think about what we've accumulated so far. We know the resulting acceleration. So what's happening here is the guy's going to accelerate down. He has a force, again, it is gravity this time. So it's gravity is pulling him down, friction's trying to slow him down, and the resulting force is the acceleration that he experiences. So let's just write that out. So we have his weight component, which is propelling him downward, minus the friction will give us our resultant force. Okay, so we've calculated his weight component is 234.625 newtons. We still don't know what friction is. I'll just put it in as an F, little friction. But we do know his resultant force. And we know that because he had an acceleration of 2.9, I'm sorry, I've gone off the page there, 2.9768 meters per second squared. That's from earlier when we calculated the resultant acceleration that he physically experienced. So if you take that value, 2.9768, which is acceleration, then what I'm going to do here is, because we know force is mass times acceleration, I'm just going to multiply it by the skateboarder's mass, which was 70 kgs, to give us a resultant force of 208.376, and the difference between them is going to be the friction. So the force that was applied minus the friction will be the resultant. So I'll just do 234.625 minus our answer, and I'll ignore the minus sign, there's none that's grand. So we had a frictional force of 26.249 newtons. Okay, that's the lion's share of it. So that's, what is it, 40 marks so far out of the 56. Let's see what we need to do to get the last bits of juicy goodness from this fruit. Alright, we have the skateboarder then maintains a speed of 10.5 meters per second until he encounters a circular ramp. Why am I drawing this when it's literally there? First off, what is the initial centripetal force acting on him? Okay, well, the centripetal force is mv squared divided by the radius of the circular path. So his mass of 70 kgs times the velocity of 10.5 squared divided by a radius of 10. They've not played any tricks in this with the units. They're all in meters and stuff. So let's go 10.5 squared times 70 divided by 10. So the centripetal force is 771.75. And again, as always, don't forget your unit or just throwing away marks. Okay, what's the maximum height that the skateboarder could reach? Now, there's a number of approaches to this. You could SUV at this and have his have acceleration due to gravity working against him, but I think what's way easier, I think the most elegant approach here is to think about his kinetic energy. So when he's skating along, he has a certain amount of kinetic energy. Let's get EK. And when he goes up the ramp, that kinetic energy gets converted, he's at the height of the curve, into purely gravitational. So his kinetic energy, which is given by half mv squared, will equal to m times g times h. This is the formula for kinetic energy and gravitational potential. And straight away, the masses cancel out. So we have half of his velocity squared is equal to g times h. We're looking for his h, so let's bring the g across. So let's do it over here. Half was multiplied here, 2g v squared is equal to his height. Oh god, excuse me. So his velocity going in was 10.5 to v squared divided by 2 divided by acceleration due to gravity of 9.8 gives us a height of 5.625 meters, which seems sensible enough. Again, always run a little common sense check. If we found out that he'd gone 50 meters up, you know, it's Superman on a skateboard. If we found that he'd gone like 5 centimeters, something that's gone wrong on a skateboard doesn't have wheels that rotate. But that seems like a decent enough answer there. Okay, finally, on what is a fairly challenging question, and it looked nice at the start, sketch a velocity time graph to illustrate his motion. Okay, well first I'm going to do it how you shouldn't do it. Alright, so for velocity time, we have time along the y-axis, velocity there, we have time in seconds, velocity in meters per second. Now you'd be tempted to think of his velocity. Okay, so he's going down the ramp, his velocity is going to increase, and then he reaches the bottom and it's going to go just flat, and sorry, it'll be remaining at the constant speed velocity, and then he's going to go into the ramp, so his velocity is actually going to decrease until he reaches rest. You'd be tempted to do that, and that's most of the marks, to be fair. But looking at the numbers and being a bit more exact, he was accelerating, but then when he came off the ramp, he was doing a velocity of, 12.2, but when he was doing this steady skating along, he was doing 10.5. So there's actually a bit of a little dip there. So your graph is looking, instead of just nice and flat, at the junction there, it's a bit of a spike, then he slows down and kind of comes to a halt. Okay, that was a fairly long question. Each component is okay. I want you to get in the habit of, like, if you're doing a SUVAT, write out everything. Be specific, use your equation, rearrange, and then substitute in. If you're going down for the later part, I'd always suggest just going the easiest, most elegant route, and in that case, it's a energy conversion one. You could have gone SUVATing him with acceleration is equal to minus 9.81 in the vertical direction, but to be honest, energy conversion is the way to go there. If anyone likes, I can work out the SUVAT one, but I want to keep this video a little bit briefer, so I'm going to leave that out for now. Speaking of which, I might take a break for a moment, get myself a drink of water, and then we'll come back to question 2.